Alright, so in this problem we have a thing that's rotating. And so our first step is to figure out things about the moment of inertia, or the rotational inertia, and then we're going to do some basically rotational kinematics and F equals ma stuff. So A and B first is to figure out the moment of inertia of this whole setup. So the first thing, we have to deal with the rod. We need the rotational inertia of a rod of about an axis through its center. So that's like if the rod is like that, rotating about the point right there. And this is length L and mass m. And so this, since it's not a collection of point masses, it's an extended object, we have to use the integral form of the moment of inertia calculation. We are given the results, so we know what we're trying to get to, but we're going to have to set up the problem appropriately. And so to solve this, we need to figure out what dm is, right? We can't do this integral over bits of mass. We can do it over bits of distance, though. So we are told the rod is uniform. So that tells us that the ratio between the total mass and the total length, and the tiny little bit of mass dm, and the tiny little bit of length dl that it occupies. Actually, that should not be dl. dr, right? Where if I draw on the original rod, right, this axis is the sort of r direction to match up, and this just basically means we're breaking up this rod into lots and lots and lots of these little chunks in the length r. And the reason that I can write this relationship right here is that it's basically a statement of proportionality. The total mass divided by the total space it takes up, because it's right, rods are the roughly one-dimensional approximation, is equal to the tiny little bit of mass in the proportionally tiny little bit of space. Right, that's all this is, proportionality. And this is, you're only expected to be able to do this for uniform objects. This is really the relationship to remember. It always looks like this, always. Now we can rearrange, so we get dm is m over L dr. And now we can substitute that in right over here. So the other thing for our integral is we have to put, this is a requirement, we have to put the r equals 0 in the point that it's rotating around. So this is L over 2 and negative L over 2 on the other side. So if we're going to add up all the little bits of mass, we don't go from 0 to L, because that would mean we're rotating about an end. We go from negative L over 2 to positive L over 2. R squared stays the same, m over L dr. Alright, so now we can actually kind of solve this. M and L are constants, they come out, and we have to integrate r squared dr with those endpoints. So m over L, r cubed over 3, and we evaluate that, negative L over 2 to L over 2. So we plug that in, m over L, actually I'll move the 3 out. So we have L over 2 cubed is L cubed over 8 minus a negative, right, because it's cubed, so we still are left with a negative 1, L cubed over 8. Right? So those combine, we get 2L cubed over 8, or L cubed over 4. And we can cancel some of these L's, and the 3 and the 4 combine to be 12. So mL squared over 12 is our final answer. And that is indeed what we were hoping to show. Okay? So the thing boxed in red, this is the big step. Everything else is just a bit of calculus. So for part B, now we're taking that rod that we just calculated the moment of inertia of, and we're putting it with a hoop. And we want to know the total rotational inertia of that combined thing, right? A hoop and a rod. Right, so it's, to make sure it's clear, right, it's just the kind of like that. Right, so it's a hoop and rod. And so to get this, we're allowed to remember some stuff. If you don't remember, this is another place where, again, you might be given it, sometimes you are, sometimes you're not. The moment of inertia of a hoop is mr squared, where r is that, right, the radius of the circle. So in this case, it's ml over 2 squared, ml squared over 4. You don't need to derive that one from scratch. Again, a lot of times in tests you are given that, and you just need to show how to combine it. But this time you weren't, so you hopefully would remember that. So then we have to remember that since moment of inertia is already just a sum, we can do the sum sort of piece by piece, right? I rod, which we just calculated, and then add it to the other piece that we've added up all the bits of, the I hoop. Right? This is just sort of breaking the sum up into two easy to calculate parts. Right, so we can do that. We combine. So if we get a common denominator, we can have a 12 and a 3 there. Right? So that is 4 ml squared over 12, or ml squared over 3. Right? That's the combined rotational inertia. Just add up the rotational inertia or the moments of inertia of each of the pieces. Right, so that's A and B, right? That's the kind of the calculus side of things, or the math-specific side. Parts C, D, E, and F are physics, specifically sort of F equals ma and kinematics. Okay. So, for parts C, D, and E, you really have to solve them all together. You can't get any one of them without kind of setting up a system of equations that would help you get all of them. So the way that to do this, you can get the answers in any order you want, whatever sort of variable you want to solve for first. But there's two things that you need to be able to solve this. Right, because we're being asked for 3 unknowns, and so we need at least 3 equations. There's 2 physics ones and then 1 sort of mathematical relationship. So, right, we have our hoop and rod, and a cat hangs from a string. Right, my cat is now a square block and falls down. Right, so it's accelerating downward. The hoop starts rotating with angular acceleration alpha, and we want to know how to describe sort of what's going on. So, the first thing we have to do is take the free body diagram of the cat. There's a tension that pulls up on the cat, and there's a weight that goes down, and that describes the cat's acceleration, linear acceleration A. The hoop has a tension that pulls on one side. There's a sort of a normal force that is like the pivot where it's like mounted, the axle. And there's a weight of the hoop and rod. Right, so I should all subscript these to indicate that they're not the same, but the different weights. Okay. And because the string is not going to stretch or anything like that, we know there's a relationship between the linear acceleration and the angular acceleration, which in this case, since r is L over 2, that. Okay, so now we need to actually start writing equations. So for the cat is moving linearly, not rotating. So we're going to use F equals ma. And so the net force, we're going to call the downward direction positive, because that's the direction it's moving in. So the cat is mass m, right, same mass, g, minus the tension equals ma. Right? That's an equation that describes the motion of the cat. Now we can describe the motion of the rotating rod hoop thing. Since it's rotating, we have to use the rotational version. And we just calculated that moment of inertia, so we'll be using that result. But first we have to figure out what the net torque is. Since it's rotating about its center of mass, neither the normal force or the weight provide a torque. The only thing that provides a torque is the tension, which is a distance L over 2 from the center, and it's perpendicular, so sine theta is 1. We calculated the moment of inertia, that, and we know that the angular acceleration is related to the linear acceleration. So we can, I'm going to leave it as alpha for now, so we can combine these kind of however we need to. But here's, right, in orange, I'm going to box the 3 equations that we need. 1, 2, actually I'm going to rewrite that one to make sure there's no sort of extraneous stuff. Right. So these three equations, there are three unknowns: the tension, the linear acceleration, and the angular acceleration. And so we can solve those in any order that we want. It doesn't matter, right? But in the end, we're going to get those three values. That's parts C, D, and E. So let's work kind of through that. So the first thing I'm going to do, I'm going to substitute this in, no, I'm not going to do that way. Substitute this in there. Or no, I did want to do it that way. Yeah, okay, so back where I was. I'm going to do that. So this is alpha equals 2a over L. So we're going to clean up this equation. So T equals ml squared over 2ml squared over 3L times 2a over L. So L's all cancel, and so we get 4ma over 3. So now we know what the tension is. I'm going to put that right there. So mg minus 4ma over 3 equals ma. We can cancel mass everywhere. Put the stuff with acceleration together. So g equals a plus 4/3 a. So that is 7/3 a. Or, and I'm running out of space, but I'll try to do it here at the bottom. Or a equals 3/7 g. Okay, and so that gets us the answer actually to part E, the linear acceleration of the cat. So you notice I'm not doing these in the same order, but it doesn't really matter. So now that we know the linear acceleration of the cat, I'm going to move to another page to do this calculation, but I'm just going to plug that right in there to get alpha. So alpha equals 2a over L equals 2 times 3/7 g over L is 6g over 7L. All right? And that is the angular acceleration alpha of the rod hoop assembly. And so now finally, let's click again, and I think I'm going to use this equation. That's probably the easiest to work with, and we're going to plug in what we know for A and solve for T. So we can rearrange that to get T equals mg minus ma, like that. Yeah, mg minus, and that is going to be mg minus 3/7 g equals m 4/7 g equals 4mg over 7. Right, and that should be the tension. And that answers parts C, D, and E. The key is to set up the system of equations correctly. The biggest part of the points, right? Those orange boxed and now black underlined equations are the three equations that describe the motion of everything involved in the problem. Right? The red stuff describing the cat's linear motion, the blue stuff describing the rod hoop angular motion, and the requirement that the string doesn't slip on the rotating hoop as it goes around. That's the black writing the top one. It goes up, then everything else is just algebra. Okay. So after descending a distance h over 3, the cat's going to let go of the string. And we want to know what the angular momentum of the cat is about point P. So there's two ways to write L. Right? And the cat is essentially a point mass, right? It's not an extended object. It doesn't really have a moment of inertia. These are essentially equivalent, but it's easier, in my opinion, to work with this one here, because it's going to be very easy to calculate the linear momentum p of the cat, and it's going to be very easy to figure out the distance the cat is from point capital P, and with that we can calculate all this out. So that'll be our approach. We're going to use that one. So our first step is to calculate how fast the cat is going, so we can use P equals mv to find the momentum. So how fast is the cat going? Well, we know its acceleration, and we know the distance it traveled. So V final squared is V initial squared plus 2A delta, in this case y, because we're moving vertically. And this is the thing we care about. So V squared equals, we start at rest. So 2A was 3/7 g, and delta y is 5L over 3. So that cancels that. So that's 10L, 10GL over 7. So now we know how fast we're going. So we multiply that by the mass, and so we're going to get P equals 10 mgl over 7. Right? That's half of it. And so I'm going to go to another page. So now we need to draw a little bit of a picture. So our hoop, so the cat grabs on, right, so this distance right here is 5L over 3. Point P is right there. This is a distance L over 2. And so we need, right, this red distance. And we also need the angle between this direction and that direction, right? We need this blue angle, drawn that badly, this blue angle theta, right? And it turns out you can actually calculate all that, but what we're really talking about when we talk about a cross product, we want the perpendicular distance between point P, that was also badly drawn, point P, and the direction of motion. Right, so we care about this sort of perpendicular distance between the two green lines, and that's just L over 2, right, the radius of our circle. So if we are to calculate L equals R cross P, that is the blue line, right, this is R, that's terrible. This is going to be RP sine theta, or P R sine theta. But R sine theta is just this part right there. So MV L, actually, sorry, we already have P, so I don't do that. So P times L over 2. And we just found P, which was, oh, I made a mistake. I have to go back. So going back here, this was V squared. So this is, so V is the square root of that. And so I'm going to have to change what my momentum is. So it's m square root of 10 GL over 7. All right, so now I can plug all this in. So m square root of 10 GL over 7 times L over 2. Right? And just kind of cleaning that up, I'm going to move over to here because I ran out of space. You don't really have to do a whole lot of combining. You can if you want, but you could just leave this as ml over 2 square root of 10 GL over 7. And I should notice that my notation is a tiny bit sloppy here, right? This is angular momentum, and this is a length, even though I've written them with the same letters, because cursive L's tend to be sloppy for me. So don't get those things confused, right? We should have been using, right, this kind of cursive L to differentiate. Okay, and so that's the answer to part F. The bulk of this problem is definitely in part C, D, and E, and being comfortable solving that system of equations.